So next talk is by Javier on unsupervised classification of planning distances.
Is this one? Okay, maybe I just. So good afternoon. I'm Javier Segovia-Aguas, and I'm going to present unsupervised classification of planning instances. That is a joint work with Sergio, Jimenez, and Jonsson. So, to start in the learning setting, what we expect from that is that to get some kind of output that is an integral value for classification, or maybe some kind of real value in the case of regression tasks. But what is the hot topic now is like how can we get some kind of more informational output? So how can we get more complex structural information from inputs into outputs? So, and this is what we call structure prediction. So our work is re-inspired in these two works, because they are really amazing, because they can synthesize programs in an unsupervised way to get these more structured outputs, so they can draw some pictures from just some information that is not classified by default. So. And our motivation is how can we use this kind of approach and move it to the classical planning setting. So we can understand these inputs for running a set of instances of classical planning instances, and we can get this structure prediction as a generalized solution for this set of planning instances. So instead of classifying all these instances by features as we do in learning, we want to classify by the solution of the instances. And instead of getting a specific class label for each one of these instances, what we want is to get a generalized solution for these instances. So to put in an example, we have a grid and we have an agent centered, and we may have a goal in a vertical line. So the goal can be any up cell or any down cell. So a classical plan will be something like, I want to move up, or I want to move up twice, and I want to move down, I want to move down twice. And a generalized plan will tell you like, move up until you reach a goal, or move down until you reach a goal. In the same way, we can do it for an horizontal line. So we can move left twice, right twice, and the same will be like in the generalized plan. So we move left until we reach a goal, or we move right until we reach a goal. What happens if we have the two kinds of task? So now we have some task that is related to a vertical line, some task that is related to horizontal lines. So there is some structure. There's some structure in that domain, and that can be classified into different kinds of solutions. So then is when we need the structure prediction. So we can classify this into some kind of a generalized plan for horizontal lines or vertical lines, or maybe into 4 different classes. Like I want a generalized plan to going up, a generalized plan to going down, another to going left, and another to going right. So the main contributions of our paper is that classical planning offers this alternative way to synthesize programs for this structure prediction. And our planning programs are more expressive than the preceding ones that synthesize this program. So a second contribution will be that we can automatically cluster all these planning instances into planning programs with an off-the-shelf classical planner. But our programs are deterministic rather than probabilistic. So this is the model we use as classical planning, and we apply some extension of conditional effects to allow the branching and the conditional loops. And for generalized planning, what we have is a generalized planning task, and we understand a generalized planning task as a set of planning instances where each one of them shares the same number of fluents and actions, but they may have different initial and goal states. So actions may have these conditional effects as we introduce, and a generalized plan, we consider that solve the generalized planning task if it solves each one of the classical planning instances it contains. So this could be a nice example for that. Like we have different initial states in the grid, and we want to move to different locations. So a generalized plan will be like move from any arbitrary position in a grid to another arbitrary position in that grid. How we represent this? We represent this by planning programs, and with this a planning program, it's just that. It's a program, like for example, in this example, that you are in an arbitrary position in a grid and you want to move to the 0, 0 cell of the grid. So this solution can be represented by this program that is composed of 3 kinds of instructions. The sequential instructions, we get this from the original domain, like decrease x or decrease y. The conditional go-tos that are used for some kind of ifs or some kind of whiles, where we move to a specific line if some condition is not holding the state. And a termination instruction, that is, if we achieve this termination instruction during the execution of the program, it means that we have finished and we reach our goal. So, talking a little bit more about our contributions. To understand the classification of planning instances, we have to introduce this unsupervised classification task. And as we mentioned, they share the frame. So the frame is the same set of fluents for each one of them and the same set of actions for each one of them. Then we have a set of unlabeled planning instances. That means planning instances that are to be classified. The definition of this is the same as the definition of a generalized planning task. So it's just a set of planning instances. And then we provide an extra number that is the number of clusters. So we have to specify exactly into how many clusters we want to classify all these planning instances. Here we have another example of a grid where we have 2 instances that wants to move to the 0, 0 cell and other 2 instances that want to move to the top right corner of the grid. So once this is introduced, now we can talk about the model. So what is a model of the unsupervised classification task? Is the set of the resulting planning programs. So each one of the clusters we have, if we say that we have 2 clusters for the previous example, it means that we have 2 planning programs that can solve this solution. So we can classify either a planning instance into one of them or into the other one, as is shown in the picture below. And then another thing is that we have a non-deterministic choice function. So we have P0 that the only purpose is to select which planning program is going to solve my planning instance. It's if the model is provided, it has to find this planning program. But if the model is not provided, it has to select the planning program, and execute it at the same time. So, for example, f, the function f for instance 1 and 3 will be classified into one cluster, like move to that cell, and the instance 2 and 4 will be classified into another cluster to move to the top right corner. So now we can do 2 kinds of tasks. Once we have defined this model, we can run 2 types of tasks. One is to compute a valid model, so to create these planning programs that are for each one of the clusters. And the other is to determining a class label of a specific planning instance given that we know the valid model. So to compute a classification, to compute a valid model, what we need is the unsupervised classification task we already introduced, and we compile it into a classical planning problem. For that, we need this number of clusters and the number of program lines that we can use to program each one of the planning programs we have for each one of the clusters. And then we do some kind of extension that I'm not going to talk too much about this. You have it in the paper, about the fluence, actions, the initial and the goal state. So all these things are compiled into this classical planning problem, and then we just can run any generalized planner to get some kind of generalized plan, and that's all. So about determining class labels. So the aim of determining a class label is just that we have a new planning instance that is not in the set of the original unlabeled set of planning instances. And we want to know which planning program can solve this planning instance. So we have to compile it again into the unsupervised classification task. So we move it also into a new classical planning problem. And now also we have the valid model. So we just have to execute this planning program into the valid model where we have all our planning programs already programmed. And we just have to execute then the F. This F function is the one that will give us the correct class label for that planning instance. That at the same time is like saying which planning program solve my planning instance. So class label and planning program is the same in that way. So this is an example of how can we determine a class label. Maybe it's quite complex, but we have a planning frame that is basic Boolean functions like and or not, for example, that can be applied to a Boolean variable. And then we want to perform two types of tasks. Like I want to assign this Boolean variable to the other or in the opposite way. So we can understand this as a two-cluster problem. Like I want to do this task or either I want to do this other task. So what we expect from here is that the planner will find the correct solution to one of the tasks and the correct solution to the other part of the task. And the planning instance that we provide is we have x1 that is 0 and x2 that is 1, and we want both to be 1. So this is the same as saying I want to assign x2 to x1. So this could be a valid model to determine this class that is actually the model that the planner finds. So an intuitive way to do the assignment of one variable to another Boolean variable and in the opposite way is to first execute an and then execute an or in the opposite way. So we keep one of the values until the other one. But the planner, what it finds, it's something different. So it finds two planning programs that can solve all the combinations of the inputs, as we can see in the table. But parts of the solution are into one planning program, and parts of the solution are part into the other planning program. So this is clustering in a different way as a human could cluster. So getting the class label for that, for the previous planning instance, like I want to assign x2 to x1, given that x2 is 1 and x1 is 0, will be the second input and will be classified into P1. So both values will be 1 after the execution of the planning program. So it will label the class as it will label the planning instance as the first class. So talking a little bit about the evaluation, we have run two types of experiments. One for computing a valid model, and the other to determine the specific class. So for that we have three kinds of domains. The grid domain, as we show some examples, where we want to learn an horizontal vertical line. Quadrant, where we want to go to some specific corners of the grid. List, where we want to visit in a data structure that is a list some nodes, or even all the nodes, or the even nodes, or the odd nodes. And the Boolean, where we have some domain where we can execute some Boolean functions, and like assign or nor or nan, and classify into this task. So the next values are just some information like how many planning instances we are providing to learn these clusters, how many clusters I want to classify it, how many lines I want to program, and the performance over FD. And about determining the class label, what we have used it is, as machine learning does, is some kind of testing. So now we have some valid models. Now we want to test it into another kind of planning instances and check if they classify it correctly or not. So for the grid and list that are the same domains, we compute the valid model and then we run it over different planning instances that are not part of the original unlabeled set, and it classifies all of them correctly. And also these planning instances are a little bit harder to solve as a classical planning problem. And for the pointers, for example, it's a domain that we created to execute different kinds of tasks, like find me a number in an array, do the reverse of the array, or select a specific number in an array. And this is really hard to compute as a valid model, but if we provide this valid model, what we actually can do is to determine a class label for a specific planning instance. So we provide the different planning instances over this domain, and it classifies it correctly in each one of them, like find the number of occurrences of some value, reverse the array, or select with the non-deterministic choice of the planning program. So to conclude, we have a novel compilation with unlabeled planning instances that can be compiled into PDDL. We can compute valid models. We can determine classes for these planning instances, or even new ones. And talking a little bit about discussion, our solutions are compact and readable, so anyone can interact with them, and are created into different clusters. So about the M value, if it's lower, it could affect finding a solution. And for larger M's, the problem is that we could overfit planning instances. Also talking that our model is noise-free, so we cannot compete with the state-of-the-art machine learning techniques. And as future work, we can understand this kind of work as a way to represent grammars. So we can see each one of the planning programs as a rule to execute in a grammar, and the full set of planning programs as a context-free symbol. So we can represent all these rules for this context-free symbol into a grammar that is a paper already accepted in ICAPS 17. And also, as a future work, we know that planning programs needs some scalability. They have some issue of scalability. So we have to find some kind of criterion to improve it, or maybe create some new heuristics, because it's a very specific structure that where heuristics are not helping too much. So thank you. If you have any question.
Questions? So I have one. In the results, I think I've seen N was the number of instructions per program.
No, N was the number of lines per program. We have to say how many lines you can program for this. It's something already done last year for planning programs.
And I've seen that most of them are between 2 and 4. So have you tried to? So it's because the domains are easy to.
Yeah, some domains are easy, but the problem is that in last year for planning programs to create one of them, it was it's exponential, it's combinatorial in the number of lines you are giving, so you have to take care of this bound. And now we are multiplying this bound by the number of clusters. So now it's more complex, because we have the same number of lines, but for each one of the clusters. So you have to program everything from scratch. So you have to take these bounds as a multiplication of both. So it's much more complex. We have improved it a little bit, but still it's not enough. So for that reason is the issue of scalability.
Okay. No questions? Okay, let's thank the speaker again.